In this podcast, we're going to talk about rate laws. All right, but first, a little review. Remember that we're in kinetics. And first, let's remind ourselves that about what a rate is. Kinetics is the study of rates of chemical reactions. Well, what actually is a rate? A rate is how fast a reaction proceeds from reactants to products from beginning to end. And how is a rate determined? Well, we're going to have to determine that experimentally by measuring the concentration of reactants over time with varying starting amounts of reactants. Okay? Um, each reaction is going to have its own equation that gives its rate as a function of reactant concentrations, and this is what's called the rate law. In order to determine the rate law, we have to measure the rate of the reaction with different starting concentrations. A rate law is going to show us the relationship between the reaction rate and the concentration. Whenever we're talking about reactants that are in gas form, gas phase, we're going to use partial pressures instead of concentrations. The equation for rate is rate equals K times the concentration of reactants raised to an integer n multiplied by the concentration of products by the second concentration. If there's a second reactant, B would be your second reactant here. So it would be like A plus B goes to AB. That would be a good equation for this. So only reactants are going to appear in your rate equation. N is going to be either 0, 1, or 2, and it represents the order of the rate. And we'll find out more about that in a minute. K is a specific constant that is specific for each reaction. It also is temperature specific as well. To determine K, you have to do it experimentally, so any K values we use will have been determined experimentally at some point. And like we've already stated, it is unique for the reaction and it changes with T. All right. Oh, snap. How you like that? The thing just went like 8 slides ahead. Aha, I had my hand on it. Okay, backing up. All right. The concentration of the products don't appear in the rate law because we're talking about an initial rate. And initially, you're just going to have reactants. You're not going to have made any products yet. And then the order of the reaction has to be determined experimentally as well. You can't just get it by looking at an equation. You actually have to do a little bit of lab work to actually determine these things. So all data we use will have been tested in the lab as well. All right, there are different types of rate laws. There's a differential rate law and an integrated rate law. The differential rate law describes how the rate depends on the concentration, and the integrated rate law describes how the concentration depends on time, so how it changes with time. So in number one, we're talking about the rate and concentration, and then number two, we're talking about the concentration and time. You always have, if you have a differential, you have it integrated, you can go back and forth, and they help us to better understand the mechanisms or how reactions happen. The rate laws do. All right, first let's start with writing a differential rate law. All right, so our problem is going to be write the rate law, determine the value of the rate constant K and the overall order for the following reaction. So you're given the reaction of NO and Cl2 goes to NoCl. All right, and you see that you have experiment 1, 2, 3, 4. So these are 4 different experiments were run, and you see the starting concentrations of both reactants, and you see the rate that it gives. Okay, well, what you want to do whenever you're trying to do this, we are trying to find out the exponents, basically. If you look at experiment 1 and 2, you see that in this experiment, Cl2, between these two experiments, the rate of Cl2 does not change. So because Cl2 is not changing it allows us to look at what's going on with NO. So by finding two equations where Cl2 is constant, we can ignore it completely, and now we're just going to focus on NO. So you see that NO goes from 0.25 to 0.5, and that the rate goes from 1.43 to 5.72. Okay? So NO is doubling, and the rate is quadrupling, which means that our reaction is second order. Okay? Because if you have 2, so this was times 2, so if you had 2, and then you raised it to the second power, that would be quadrupling over here, because 2 squared, okay? So x is really 2. Okay? Now let's look at our Cl2. Okay, so we want to hold NO constant, so we see that equations are experiments 1 and 3. NO is held constant, so we can look at Cl2 and what's going on. So we see that Cl2 is doubling, so you have a concentration of 2, and you see that the rate is also doubling, which means that you are first order, because double, which is 2, raised to the 1 would be 2. Okay, so that means our equation with respect to Cl2 is just 1, so we don't even really need to write it. So here's our rate equation right there. Okay, now we need to find K. All right, to find K, we're going to have to do a little bit of equation manipulating. All right, so here is our equation. So we know that the rate is 1.43 times 10 to the negative 6. So we're plugging that in for R equals K, we don't know. The concentration of NO was 0.25, and we found that that was second order, so it gets raised to the power of 2. And then we know that the Cl2's concentration is 0.25, and it just gets raised to the 1. Okay, so now we're going to plug and chug and do this math real quick. All right, 0.25 squared is 0.0625, and then we got to multiply that by our 0.25, and that gives us, let's see here, 0.015625. Okay, and that's multiplied by K, so we got to divide by this number to get rid of it and get K by itself. So we're going to do that on both sides. Okay, and then you just got to plug it in the calculator. Make sure that you put this top number in parentheses or it'll get you all messed up. Alright, and we see that K is equal to 9.152 times 10 to the negative 5th. Okay, so that is our value for K right there. Alright, how do we determine the overall order for the reaction? Well, to determine the overall order, you want to add the exponents. So you want to add the order of the first concentration, which was 2, and the order of the second concentration, which was 1. So 2 plus 1 will give you 3. So the overall order for the reaction would be 3. Alright, in this problem we see that we have the rate of disappearance of Br minus, and we see that it's 1.5, and it wants to know the rate of appearance of Br2. Well, you guessed it, your great friend Mr. Stoichiometry is back, so we just need to do a little stoichiometry to figure this out. So we know this is Br minus, and we know that Br minus, there are 5 from the balanced equation. And we want Br2, and we know that there are 3 of those. So a little simple stoichiometry gets that. So 1.5 times 3 divided by 5. Which gives us 0.9. Oh, there he was. Couldn't find him. Alright, rate of disappearance of H+. Okay, well, H+, okay, is going to be disappearing just as Br minus disappears. So 1.5 mole Br minus times 5, and then 6 of those for every 5 Br minuses, so 1.5 times 6 divided by 5 gives us 1.8. Oops, hard to see this little sucker. All right, rate of disappearance of BrO3. Okay, so we've got 1.5 Br minus, and 5 goes on bottom. All right, and BrO3 is 1, so it's 1.5 divided by 5 gives us 0.3. And rate of appearance of H2O. So we've got 1.5 times 5 and then 3. So this will be 0.9. Okay, and that's how you do a problem like that.